Hi guys, this is you speaking again. Relays, PCB relays. I'm opening today a new subject about printed circuit board relays, and we're going to use them for some project later on. The relays were invented about 200 years ago, and you can imagine that we face a really broad subject. The number of applications for relays after so many years, it became absolutely unbelievable. From simple controls of a light, what we're going to do in a demo today, to very complex applications in nuclear plants where they can stand in front of semiconductor devices because of the radiation. They're considered even more reliable. So what are the relays? Simply put, they are electrically controlled switches. But these are not the only electrically controlled switches. What about the diodes? The diodes are the simplest ones because the only way you can control them is that depending on the semiconductor they're made of, as soon as the voltage across a diode goes over the forward voltage, then the diode starts conducting. But there are better switches than a diode. The transistor. In saturation, the transistor works like a switch. So as soon as you put a voltage over the base of the transistor, you get a conduction, a perfect conduction between collector and emitter. So like a switch. Another one is the thyristor. As soon as the voltage between the gate and the cathode goes 0.7 volts, then the anode to cathode starts to conduct. And then the TRIAC, made of two thyristors against each other in parallel. So the TRIAC was designed especially to drive AC loads because the two thyristors against each other are going to conduct each of them during one alternance. So then I've made a short list of electrically controlled switches. Why then we talk about the relays? What is the advantage of the relay over the other ones? Again, simply put, the transistor, which is the most common electronic switch, it cannot deal with AC loads. Even if it can amplify AC signals, like it happens in all the sound amplifiers everybody uses, but the load is not an AC one. The TRIAC, it can take an AC load, but the standard or the traditional electromagnetic relay, it has a very interesting property. Being made of two things, coil and contacts, that's a perfect insulation between the two parts, the control, which is the coil, and the output, let's say, which is made of contacts. So because the two parts of the relay are electrically insulated from each other, then you can energize, let's say, the coil of the relay in DC, which is the most common way to use it. But the contacts at the output of the relay can be used either to drive a DC load or an AC load. So then I have one right here. If I'm taking it out of the plastic box, we can identify easily the parts of the relay. So let's start with the coil. The coil is what's covered here by the yellow sticker, made of a very thin wire. Take a look how thin it is. Thousands of turns inside. One end here, one end of the wire here, and the other end on the other side over here. So imagine, because the wire is so tiny, it's so thin, you don't need a big power to energize the coil. Actually, it's asking for a very low power, and you can realize that by just considering the amperage any coil needs, and you measure the amperage in tens of milliamps. Just that. The second part is made of the contacts. Here there is a long plate, this one, This is called the pole. And this is the actual moving part of the contacts, because you can count here one contact on my right, one on my left, and the long plate in the middle. So as the plate, when you do nothing, you don't energize the relay yet, the plate is touching the contact on my right, this one is called normally closed, because normally when you don't energize the coil, it is closed. The other one, it's an open circuit, it's called a normally open contact. And when the plate in the middle, the pole, is moving, the normally closed contact is opening and the normally open contact is closing. That's how the relay is operating. How this plate is moving, though, is simply because in the moment the coil is energized, the core of that coil is made of iron, so the whole assembly becomes an electromagnet attracting the metallical support of the plate. So then suddenly the plate is going to move as soon as the coil is energized. It's very quick. So exactly one like this I have in the device, and we can watch what happens when we're going to energize it. And you're going to also hear the sound. So take a look. As soon as I touch and I close the contact to energize the coil, that plate right here, you can see now, is the only moving part. It's toggling between the two other contacts. So here is on my left the normally closed. When I energize, the coil is opening. On the other side is the normally open. When I energize, the pole is touching it. See? This is how it's working. So remember, coil and contacts. Because of this, we're going to move now over the screen to discuss a bit about these contacts and the arrangements. Okay? So we have them right here. What I represented here in a yellow square, in a yellow rectangle, is the pole. I made it in red just to make sure we get this as a moving part of the relay. And the wire coming out of this pole is called common, so the letter C stands for common. And the other one is the normally open contact. So when the coil is energized, then that pole is moving and closing the contact. Imagine here in series with the normally open, you have the load. So by touching the pole to the normally open, you're going to energize the load. Now, the one I put in a blue circle right here, it's another kind of arrangement. As you can see, this is a complete arrangement of the contacts. You have the common, and you have the two other contacts, normally closed, normally open. So the common is toggling between the other two. I call this a full group of contacts. This is an incomplete one because the normally closed is missing. But both of them are very common on relays. Another one here is made of two groups of contacts. One group here and one here. The dashed line or the dotted line right here in the middle just says that the two plates, the two poles, are moving at the same time both. You cannot move only this one and not moving the other one. If it happens, the relay is defective. Has the name of the arrangement of these contacts inside the relay. The first one, the one in the yellow rectangle, is called SPST. SP stands for single pole. There is only one pole moving. SP. For the second one is also SP. There is only one pole moving. But for this one is DP because there are two poles, double pole. Now here it says ST. Here it says DT. DT stands for double throw. The double throw stands for the number of options between which the pole is moving. So you have two options here, this one and that one, so it's a double throw. Here is a single throw, because the other throw is missing. So single pole, single throw, single pole, double throw. The interesting thing is here, because it says double pole, which is right, there are 2 poles, but it says double throw, it doesn't say 4 throws. Because what's written here, it refers to how many throws or options you have per pole, for each pole. So for each pole, you only have 2 options. This is why it's called double throw. So far, so good. So this is the standard arrangement. Now, where you can find this one? You have to consider first that in any relay, there is a coil, because there is no way a relay can work without the coil. So then, supposing you have coil and contacts, take a look at that arrangement, because here we represent the 2 wires coming out of the relay coil. So here you have 2 wires here and 2 here. So the relay is going to contain 4 wires. I have one right here. This one, if you take a look, you're going to find plus and minus, exactly like here, plus and minus. These are the 2 legs on the 2 screws over here, energizing the coil. On the other side, you find one pole, this one, and a normally open contact. So that's exactly that arrangement over here. Okay? So in total, you find 2 screws for the coil and 2 other screws for the contacts. Total is 4. That's the kind of relay. Additionally, this one here, which is a PCB relay, can be easily placed on a DIN rail. We're going to talk about that soon. I'm picking up another one. Let's say I'm picking up this one. If you take a look at it, it has 1, 2, 3, 4, 5 contacts. These 2 ones are for the coil. So how many remaining? 3. It has 3 contacts because it's that arrangement here of contacts with the coil. Okay? So always from the total number of contacts, like 5 here, you subtract 2 for the coil. And the remaining is telling you how many contacts it has. 3 contacts is making a full group of contacts over here. So that's how you know. So far, so good. Now I'm going to use for the relays 2 kinds of classifications. There are a lot of classifications for the relays because there are so many. But for the purpose of using the PCB relays, I have 2 kinds of classifications. The first one is to make the distinction between, give me a second, to make a distinction between the traditional electromagnetic relay, obviously, as we discussed before, and you can see it has moving parts, and solid-state relay, having no moving parts. This one contains TRIACs. So maybe the name is not very proper because it's not a relay actually inside, but when it was called solid-state relay, it was because of the function. Why? Because it is an electronically controlled switch, exactly like a traditional electromagnetic one. And it's called solid-state relay again because it does not have physical contacts inside. It's made of semiconductors. And I can mention 3 kinds of semiconductors if you want. An optocoupler to make the insulation between input and output, a phototransistor, and then the assembly made of TRIACs, which is what's going to the output. So again, first classification, electromagnetic relays, solid-state relays. The second kind of classification is for the electromagnetic relays, standard ones, because this one, I just took it out of the box. So if I remove the plastic box, it's like an open relay. I can touch all the elements I want, the coil, the contacts, and so on. But then you have this kind of relay, which is completely sealed, and this is actually what we call a PCB relay, printed circuit board relay, because it can be placed on a board and soldered. Or, even better for our projects, you can have this kind of arrangement, this one, where the relay, if the pins are placed properly, it can be placed on a breadboard, so we can check our projects before dealing with the final object. And that's a very friendly arrangement for us. It's completely sealed. You don't have to deal with the elements of the relay, excepting to take a look in the specs to find out what are the pins for, okay? How to connect the pins. So, 2 kinds of classification again. One classification says electromagnetic versus solid state. Second classification for electromagnetic relays, basically, between classical construction and PCB relays. The PCB relays, by the way, they have very tiny terminals. This is why they can be placed on a breadboard or they can be soldered, versus the standard electromagnetic relays, which are used in most of the cases placed on a socket. So when you really have to deal with the wiring of the relay, you're going to connect thick wiring out of it. Why thick wiring? Because most of the relays like this one, they can draw over 10 amps. So for big amperage, you need big wiring. And if I can show you what is the equivalent for a printed board relay, take a look how thick the wiring has to be in order to sustain the maximum amperage the manufacturer gives you in the specs. Okay? So this is about the connections for a standard electromagnetic relay. Additionally, I can show you another one right here. This one has a lot of contacts. If you just take a look, there are 1, 2, 3, 4 groups, 4 complete group of contacts. And it's practically impossible, even if you think it may be soldered on a printed board, it's practically impossible to draw the proper thickness of the wiring for this one on a printed board. This is why they are practically used on a socket. And if I plug it on a socket here, then I place the stoppers in the top of it, so it's going to prevent it from popping out accidentally and to resist the vibrations. And that's the way it is used. So far, so good. Now I'm going to focus on the PCB relays. So I pick up the one we discussed before with 4 contacts. It's an industrial one. If you place it here on support, and then by having it on the support, it doesn't fall anymore. That plastic support has only one purpose: to allow you placing it over a DIN ray, so you can move it along and placing a lot of other similar relays one after other. Okay. The next one here, this is a bit more interesting. This is also an industrial relay. This one is designed for 24 volt, exactly like this one. So both of them are designed for 24 volt. Okay, that's the industrial DC voltage. But interesting thing, unlike the other one which is soldered, this one is placed on a socket. It's a very special socket. It's practically impossible to find it as a hobbyist, let's say, but it's an industrial socket. And then when you place it on the socket, you can put the mechanical stopper over it. Okay. What's interesting about this is that if I'm ordering another one, I put a label over it because it's not easy to guess the coding without a strong light. This one is a similar relay at 5 volts. And it has exactly the same footprint as that one. So if I'm just removing it and replacing it by the new one, and I place the cover in the mechanical clip on the top of it, now I have an assembly I can use for 5 volts instead of 24. Because both of them, they use the same socket. So in the same way, I can use one at 12 volts instead of 5 or 24. So that's also very interesting. And the third one I'm showing you is this one. It's made by the company Finder. And the big blue body here is only to give you contacts. They even show you on the blue body here the wiring arrangement. You have access to screws everywhere, but the actual electromagnetic relay, there's not a solid state, there's an electromagnetic relay, is right here in the top. the coil is made for 12 volts. So this one is for 12 volts, but I can order another one for 24 if I want, okay? So what's interesting about it is that you can remove it from the top, from here, take a look. I remove it, and it has 5 contacts. The coil plus a full group. I put it aside. I ordered another relay, which is identical as company, is the same company Finder, but this one has the coil of 5 volts, not 12 volts. So because it has the same footprint as the other one, I can put it here and place it over the socket, and then it's gonna work as a 5 volt relay instead of 12 volts as the other one. Guess what? I can have another one at 24 volts. I remove it again, and this is a very special socket, this one here. So the relay unfortunately won't fit on a breadboard, but because the pins can be soldered, you can either solder it on a board or placing it in a special socket like this one, okay? So that's how you can use it. You just push it, so then the stopper goes over it, preventing it from fall. That's called the sling relay because it's very narrow, okay? So these are the kind of arrangements you can find, and obviously, like the other one, it's very easy to place it over a DIN rail, so you can put a lot of them one after other, so making a big assembly of relays on a DIN rail. So far so good. And the final one I'm showing you is what you can use to expand or to extend your Arduino capabilities, because both boards I'm showing you now are especially designed to be used with Arduino boards. This one has 1, 2, 3, 4 relays, and all of them are coming with 1, 2, 3, 4 terminal blocks, the green ones, one for each relay. And obviously, if you watch over here, it doesn't matter the terminal blocks, they have 4 contacts, one of them is not in use. You're going to find the common, and then you're going to find the normally open and the normally closed. Common, normally open, normally closed, and so on. Each terminal block has common, normally open, normally closed for each of the 4 relays. These ones are made to drive up to 3 amps, okay? And I have another one, smaller footprint. Here is also designed for Arduino because you can see the long connections, the long terminals over here. They fit exactly on any Arduino board. And this one has 1, 2, 3, 4, 5, 6 tiny relays. And these 6 tiny relays are drawing maximum of 1 amp. They are similar to what we have in our PLCs, in the programmable controllers, up to 1 amp. The only drawback for this kind of board are the very tiny screws over here. You need a special screwdriver like this. This one, if you can see, it's going to fit precisely over here. Just for you to know, this is a flat screwdriver, and I can measure it. I can measure it, and it's going to be about 1.8, maximum 2 millimeter flat screwdriver. That's what you need for such a small Arduino board, okay? Very good. And now we reach actually the subject for today, the main subject for today. I prepared for you 2 demos just to show you how you can find out electromagnetic and solid-state relays and the differences between them. The first demo is using a standard PLC. So I'm picking up one of my PLCs and a collection of outputs over here. It's a standard application I use for a fountain system with 7 valves. Let's put it at work. When you start it, you can count. Here on the PLC, you can see some lights popping up. And you can hear some noise. The noise is coming from the relays inside the PLC, which are pretty similar to these ones. The size of the relays inside the PLC, they are not bigger than these. And they won't stand more than 1 amp each. So for that reason, I'm using some other external relays bigger than that because you cannot drive a standard valve with very tiny relays. Okay? And the thing is, all the LEDs monitoring the outputs, that's one of the standard features of the PLCs because each output, each input is monitored by one LED. But all the LEDs are having the same color, so it's not very easy to quickly identify who does what. Okay? For that reason, I picked up a flat cable, so I transferred the signals from the PLC in what I call an output trainer. And on these ones, each output is identified individually because each output is a different color. So you can easily watch now the pattern of what the valves are doing when closing. So easy to identify the pattern because the lights can be identified individually very easily. Okay? So far so good. You can hear the relays because all the relays are inside the PLC. So I can close it now. By the way, before I close it, you take a look here inside. I have two solid state relays, exactly the same as the one I was showing you before. I have two solid state relays too. Okay? Very well. So now I can stop it. Now we go for the demo I prepared particularly for this kind of discussion we have about the PCB relays. And the demo is made of several parts. The first part is the power supply. It's a standard power supply, non-regulated. It gives me about 12 volts. The second part is the control. One control, this one here, is for electromagnetic relay. Is the relay itself plus a flip-flop. And the other part of the block is a solid-state relay block. So the flip-flop is over here. I just improvised one to make it similar in function as the other one. So again, the power supply, the two blocks, electromagnetic and solid-state relay. Then the input block. For the flip-flop, remember that each flip-flop needs two inputs. You can call them set, reset, or on-off. So for the electromagnetic relay, the inputs are over here, on and off, on. So when the input goes on, I control the relay. So the LED is showing me the relay is actuated, and off. And respectively for the solid-state relay, on and off, on and off. Another block is the one in the middle. The one in the middle is a DC to DC converter because the power supply here, the non-regulated, is giving me 12 volt and I need 5.2 for this one. So I'm going to switch the picture over here to show you a magnified picture of the two relays. The tiny blue one, the electromagnetic one, is here. And the black one of the two solid-state relays, is over here. Now let's take a look on the body, what they printed on the body. The blue one over here is a 12 volt DC coil relay. So the information here, 12 volt DC, is for the coil. And above it is the information about the amperage of the contacts. You can use AC loads. Take a look, AC is right here. It can carry 10 amps. You can use DC voltage over here. 28 volts, don't take it literally. The industrial DC voltage is 24, but it has a reserve up to 28. Also 10 amps. And by the way, a useful information is, this is the maximum amperage the relay can stand. So never use the relay for the maximum amperage. Use a common sense rule, no more than half, okay? So if it says 10 amps, don't use it for more than 5 amps. This is a solid-state relay. It doesn't have a coil, but it can be driven at 5 volts DC. So it says here, input 5 volt DC. That's a very good quality relay, by the way. It's made by Omron. The load, it doesn't say anything about the DC load. This one cannot stand a DC load, but only an AC load, 2 amps. Anyway, the lamp we're going to drive is taking much less than 2 amps, so we have no problem with that, okay? So 5 volts, 2 amps. 5 volts, this is why I read here on the DC to DC converter 5 volts. You take it with some tolerance, now it's 5.2, it's no big deal. If I press the little button here, so this button gives me information, okay? However, the voltage for me is 5 volts for the solid state relays, and it's going to be about 12 volts for the electromagnetic. Now, let's use it. I'm going to pick up my load and connecting it here. The last element I should talk about is this one here in red. This contains a power switch. I have only one load, but I have 2 blocks of relays, electromagnetic and solid state. So I use this power switch to connect my load over each group one at a time. So now it's connected over the solid state relay. So I press on. The lamp goes on, off, on, off, on, off. Just hear it. Can you hear any sound? You can't. Because remember, the solid state relay does not carry any sound. Why? It's made of semiconductors. No moving parts. The contacts don't touch each other. Okay? Take a look. But then if I want to hear the noise, the only noise I can hear is from the electromagnetic relay. So I have to put my switch on the electromagnetic relay. So now if I use this one, take a look, electromagnetic relay. These are the 2 input blocks, the capacitive inputs. On, off, on, off. So my load goes on, but you can hear the sound. What sound do you hear? Is the sound of the contacts inside the electromagnetic relay. So remember, electromagnetic relay, solid state relay, silent, no sound. See this? No sound. Sound. No sound. This was the demo. The next video is going to be about the use of such tiny PCB relay. We're going to use one such very small relay, exactly one like this, and we're going to be able, by using it, to use a printer for 2 distinctive computers. This is going to do the job, okay? And the next video after that will be how can we check our relays, even if we don't know the specs of the manufacturer, and we can identify the terminals, and at the same time we check if the relay is good or not, okay? So, thank you for watching, and see you back for the next one.